Okay, so it's my pleasure to welcome Dan from UMass Boston. He'll talk today about symplectic resolutions of quiver varieties.
Okay. Great. Everyone can hear me okay? Is this good? I'll take that as a yes. People can hear me. Okay. I want to tell you about kind of symplectic resolutions of quiver varieties. And there's kind of two different inputs. I have to tell you about symplectic resolutions and tell you about quiver varieties. Quiver varieties can take a little bit of time, and so I'm gonna kind of push them off until the end. And in this talk, I'm gonna be kind of casually lying about the setting for some amount of time. This is actually what I think the point of a talk is you can explain your paper, but stripping away some of the details that you don't want to say as much. And so don't use any of the things I'm saying as like strict, hard and fast mathematics. If you have a statement in here you want a proof of, I can try to produce like a formal proof. But okay, let's get started. I mostly just want to kind of introduce you to who I am and kind of the way I think about mathematics. And so kind of this style will play kind of a role here. This is the first and potentially only slide in the talk where things are pre-prepared, and then I'm going to write things down somewhat slowly. But the idea here is motivation. Um, you have symplectic resolutions kind of conveniently at the center, at least at the center of this talk. And then you have on the left side inputs, kind of examples of symplectic resolutions. And then on the right side, kind of either outputs or things you can do with symplectic resolutions or ways to think about them. And so I'll just start in the top left. If you have a semi-simple Lie algebra G, you can look at its set of nilpotent elements. And if you have a nilpotent element, you can scale it by 1/2, and that's still a nilpotent element, what by 1/4, 1/8, etc. And you have this scaling action towards 0. And 0, of course, is a nilpotent element. And so this C star action scales in to kind of the origin, the 0, the most singular point. And the set of nilpotent elements forms a cone like this. The cone is singular as an algebraic variety. In this case is given by the vanishing set of some polynomial. It is an honest variety. And it has a resolution of singularities called the Springer resolution given by the cotangent bundle to the flag variety. And the main reason I want to mention this is this gives an interesting class of symplectic resolutions. And today we're going to be looking at a somewhat different class coming from quiver varieties, although there is some overlap depending on the Lie algebra that you start with. I should note at this point, at least just in words, there's a program to classify symplectic resolutions of singularities. That's a program I'm going to be discussing to some extent. And this was initiated by a number of people, but was popularized by Andrei Kunkov, who has this now famous quote referring to symplectic resolutions as the Lie algebras of the 21st century. And the point of the quote is that the classification of semi-simple Lie algebras gave rise to this kind of interesting classification of root datum and interesting combinatorics. And so it's believed that a classification of symplectic resolutions would have kind of similarly interesting kind of combinatorics underlying it, and would subsume the classification of semi-simple Lie algebras because of this relationship. But okay, this is not the only source of symplectic resolutions. One quick second source is you start with a finite subgroup of SL2C. Because it's SL2C matrices, it's acting on C2, on vectors. And then you can ask for the quotient of this action. And quotient today is going to be funny. Well, we'll define it in some different ways, but for the time being, we'll take a GIT quotient. And so you want your quotient to still have the structure of an algebraic variety and the quotient map to kind of preserve the structure. And so by passing to the algebra functions, taking the G invariants and then taking spec, you get a good quotient in algebraic geometry. So this is another nice class of symplectic resolutions where you take what's called the Duval or Kleinian singularity. You can blow up the origin kind of some number of times and get a minimal resolution. Okay, so these are kind of examples. And now if I give you a symplectic resolution, a symplectic resolution is in particular crescent, meaning it pulls the canonical class back to the canonical class. And so this is a nice property to have in birational geometry. It's not actually the direction that I kind of think in, but it's important to note with the title here, I'm going to talk about techniques for building symplectic resolutions, and these techniques should work in the crescent case as well. I'm just keeping the scope more narrow for the purpose of the talk. Okay. What is a symplectic resolution? I maybe could have started with that. It's sitting on the slide. You have a space that's almost symplectic in the sense that it's singular, so it can't fit into the traditional definition of symplectic. But on its smooth locus, it has a symplectic form. So that's already something. But the question is kind of, can you extend the smooth locus? Can you extend the symplectic form in a resolution of singularities? So the data here, I haven't written it on the slide, is you have pi. This map should be proper. So inverse image of compact is compact, and it should be a birational map. So this is an ordinary resolution of singularities. In the strengthening to symplectic resolution is that this symplectic form, when pulled back, then extends to a symplectic form on the whole space. Okay. And at this point, I should mention there's a notion of a partial symplectic resolution where this source is no longer smooth. But you can still ask that it pulls back and extends to the smooth locus instead of to the whole space. And then that would be a partial symplectic resolution. Okay, last kind of application is more algebraic, the setting of Poisson algebras. But this difference between being singular and smooth and being kind of symplectic versus having a symplectic resolution, in the algebra world with Poisson algebras, it's in a way less noticeable. So
Can it cut out for a second?
Yep.
Just cut out for the last 30 seconds or so.
Okay, I cut out starting when I was explaining the definition of symplectic resolution.
No, just 30 seconds or so.
Okay. Okay, so let me go back. I'll assume for now that this was at least decently explained, and I'll say things about it in the future. And I'm trying to explain this kind of inclusion, how given a symplectic resolution, you can produce a Poisson structure. So given something symplectic like x tilde, its algebra of functions has what's called a Poisson bracket. So it's given explicitly by given a function f and a function g, you take d of f, d of g, and apply the symplectic form. And so this is a Lie bracket that satisfies the Leibniz rule. And one useful thing you can do with a Poisson bracket, if you have one, is you can form what the physicists would call a quantization, where you start with your commutative algebra and you deform it or perturb it kind of in the direction of the Poisson structure. You get a new algebra that's now kind of not commutative. It's actually, if you just perturb it with respect to the Poisson structure, it's probably not associative as well. You have to add in higher order terms for the resulting algebra to be associative. But you can get interesting non-commutative associative algebras this way that in some ways mimic the properties your algebra functions had before. Okay, let me pause here with the motivation slide. Are there questions about this? Yeah.
So, so you're not assuming that your like X is normal or anything like that, are you?
No, this is a good question, and my X should be normal. All the examples I have in mind, it is normal, and so let's add it as an assumption. Yeah. Yeah, thank you for that. Are there other questions? Okay. Okay, good. Let's start the talk in earnest. I used to give talks as a narrative where it was like, oh, it's going to twist and turn and there will be some exciting ending. And then I realized that people follow talks less like a novel and more like a newspaper, where you're reading like the first couple lines and at some point you're going to fall off. And so more in that regard, I'll just spoil the end or what the main result is I'm trying to get to. I'll state it in this level of generality. It's just an imprecise conjecture, and then I'll make maybe some more precise versions of it. So the statement is that most symplectic resolutions are not projective. And historically, I should point out a paper of Arbo and Proudfoot. They were the first person to notice this, and they're in the kind of the hyperkähler setting. I'm actually not completely sure about the origin of the term hyperkähler, but Nakajima's original term was what was it? Hypertoric kähler, and then at some point, kind of the notation shifted. But they basically come to the same conclusion from a combinatorial perspective. Combinatorial involving zonotopes, but what's going to happen in this talk is something somewhat similar, but arguably the combinatorics are going to be simpler, or maybe at least from my perspective, they're simpler because they're already kind of known to the quiver variety world. And in the setting of quiver varieties, this is also observed. So Alistair Craw has a student, Austin Hubbard, and he was looking at hyperpolygon spaces. In each of these two versions, they have examples that can be phrased as quiver varieties. In Austin's case, the quiver looks something like this. It had one internal vertex with a bunch of external vertices. And the dimension vector was 2 at that internal vertex, and then the rest were 1s. But okay, in terms of explaining the history here, I'm getting a little bit out ahead of myself in terms of definitions. And so let me start kind of the background of the talk in earnest and just say that the update to this is that we get another class of examples that are Nakajima quiver varieties. Which Austin Hubbard had already done, but now we have a dimension vector that has all 1s, and it simplifies the combinatorics. And so it's a little bit easier to see what's happening in our case. Austin's paper is trying to do something a little bit different. We're trying to say, here's a really large class of proper resolutions for many different kinds of quiver varieties. Austin's looking at a particular quiver variety, and he's actually classifying all the proper resolutions. We kind of attempt no classification. Okay. Yep.
So this is for like all quiver varieties or just for that one, like you and Schedler yourself?
Yeah, so this this paper should ideally hit archive soon, where the exact statement is precise and clear. The point is that the example I'm going to do in this talk will have kind of two vertices, X and Y. Think of X as kind of your central vertex. And then there will be, say, 4 vertices like this. So yeah, the outline here is that we start with this particular quiver and dimension vector all ones. And as I'll explain later, there's a theta as well with value 2 at y and 2 at x, and everywhere else is -1. But we play with this setting enough to understand exactly what paths need to exist, what we need to be able to do to construct the example. So once we get this, we start you get the same statement for this one where you add another vertex and you add arrows. You get the same statement for this one where you just start arbitrarily adding more arrows into the quiver. You get the same statement if you pick any of the vertices that's not X, that central one, and you increase the dimension vector as well. So you have a fair amount of flexibility to generalize this first example. And then the paper reads like variations on a theme where we keep getting more and more general versions. But for example, any quiver on 6 vertices that then has enough arrows is going to satisfy this condition. That's one of the senses in which kind of most of the quiver varieties are going to satisfy this condition. But when you go to write things down, you'll see that you need kind of a Picard group sufficiently large, or yeah, the dimension needs to be kind of big enough, although we do find a kind of a 4-dimensional example. Okay, so yeah, the more precise statement is we do this for a large class of quiver varieties. And we have, in some sense, minimal ones like the one shown before. Okay. Good. Okay, questions up until now? Okay. The talk is in some ways flipped. It's in reverse. So I'm stating things that haven't completely been set up. Now I'm going to go back and say kind of the relevant definitions and get everyone else kind of on board. That example is going to come later. So I add a page. Okay. Okay, so stay with me if you haven't understood kind of anything I've said so far. We're going to go back to the beginning. You have Q. Q is going to be a quiver, and a quiver is the same information as a directed graph. It's just a community giving a name to something that already had a name. And so this is a good example to have in mind. For bookkeeping, when we write down the quiver, I do want to name each vertex and name each arrow, okay? And the only people that call this a quiver and not a directed graph are the people that are going to think about representations. So I can fix what's called a dimension vector D to be, say, all ones in this case. And now what the representations of this quiver are is I put the complex numbers at that vertex. I have a linear transformation. I'll abuse notation and call it A as well, to C. Now I have another linear transformation to this third vector space, and then one back like this. So the set of all possible representations looks like these kinds of diagrams in vector spaces, where A, B, and C, in this case, are just kind of real numbers. But in general would be matrices going between vector spaces. Okay? And so this is an affine space. There's nothing particularly interesting about this. It's three complex numbers. Okay. But there's an action. So I can essentially change bases at each vector space. That's a product of general linear groups in general, but in this example, I just have C star at each one of these three vertices. So three copies. And it's acting on the set of representations. And how does that go? Like, for example, if I take G1, G2, G3, and I act on the arrow A, what happens is first perform the inverse of G1, then compose with the arrow A, and then do G2. Okay, like this. And you'd act on the other arrows similarly. Okay. With this action, sitting inside here, we have a diagonal, like a C star times the identity. And the diagonal acts trivially. If G1 and G2 are the same scalar, I move them past the transformation. Because this part acts trivially, you often just quotient out by it. And so you consider PGD, which was this group acting, but getting rid of the diagonal. Okay. And the first question I want to understand about this action is, what are the orbits? Let's say closed orbits for now. Okay, good. And the reason I want to know this is at some point I want to take some kind of quiver variety, not yet a Nakajima quiver variety. Those are unfortunately kind of different things. But some quotient of this kind of affine space by this product of general linear groups. Okay. So let's play with the action and kind of see what happens. Well, if A is not 0 and B is similarly not 0, then I can act. Let's see, how do I want to do this? So I want to act by this triple, say A, then 1, and then B inverse. And so if I've done this right, the way that A is acted on is first by A inverse, then A, and then the identity. So this becomes the map 1. The way B is acted on is first with 1, and then afterwards with B inverse. So this becomes the map 1. And now this map is the product, A times B times C. Okay, so these are two kind of equivalent representations. They're in the same GD orbit. And staring at this carefully, you notice, oh, here's a perfectly good function I have on the set of all possible representations. To this pair, this triple ABC, I just look at the product, A times B times C. And the benefit of this product is that this is a GD invariant function. And using this, I can get more GD invariant functions. So taking the product, I could like square everything. And that would be another perfectly good invariant function. But there's not so much more than this that I can do. And so the GD invariants are kind of generated by this single product. I should mention, in this talk, the dimension vector is all 1s, but this kind of idea still holds in general. If you had higher dimension vector, you go around a loop in your quiver, you get back to where you start, you get an endomorphism of this vector space here at this vertex. You can always take trace of that endomorphism and get a perfectly good GD invariant function. And so maybe I should I should mention a result that this is a somewhat general phenomenon. Lebrun and Borghese. If you start with representations, some dimension vector, you look at the functions there, and then you take the GD invariants, you're going to get an algebra that's generated by the traces of the cycles. Okay. And I notice I've strayed slightly from the original question, which is that I mentioned just the case when A wasn't 0 and B wasn't 0. And in that case, you could produce like a spanning tree containing ones, and then you had all of the information of the representation just in a single arrow. But what happens if A is 0, for example? So this map is, how did I write this before? So really, if any of the three maps, but for now, let's say A is 0, now you can rescale kind of here and here. So I can act on B by maybe T inverse. I can act here by T. And then I get an equivalent representation. That has this T in it. If I take the limit as T goes to 0, this limits into the 0 representation. Okay. So I should have mentioned we're fixing the vector space at each vertex. That's kind of the role the dimension vector is playing. I'm fixing everything as one-dimensional. What I'm letting vary here are the different kind of linear transformations, in this case, numbers between them. And you can always take every linear transformation to be 0, and this gives you the 0 representation. And the 0 representation is essentially the culprit for why the quiver variety has singularities. The general linear group is always acting on it trivially. And so when you go to take the quotient, a singularity develops there. And so part of what we're going to need to do is develop some machinery to remove the 0 representation, or maybe to remove these larger representations that limit into the 0 representation. And this is what King stability does. And so that's kind of the next thing I want to mention. The narrative right now is that we can form interesting spaces combinatorially from the data of a quiver and a dimension vector. And from the perspective of the talk, these spaces being singular, it's interesting, but it's a bit of a problem. We want to resolve the singularity. And so we'll use kind of stability methods. Okay, questions? I guess I should answer my own question. The point is, you have kind of an affine space worth of closed orbits. It's in this product AB C, but when it's 0, you should take kind of the 0 representation instead. Okay. Good. Okay, so how am I doing on time? Obviously not great, but let's go ahead. So King stability. Because I mentioned the premise in words, okay, what do I really need to say here? The point is, we're going to define theta. Theta is going to have is going to be an integer for each vertex in the quiver. Theta will dot using kind of the standard dot product with the dimension vector to give 0. And we're going to use theta to rule out certain representations and form an open subset. This open subset sits inside all representations in a way that when you go to take the quotient, you get something like a resolution of singularities. Okay. But the key information is this, this kind of GD invariant open subset. And so now I'll tell you what to remove. So W sitting inside V, some representation, is theta destabilizing. If when you take the dimension vector of W, so W is some representation like before, at each vertex there's a vector space there. You can take this vector of dimensions and dot it with theta, and if you get something positive greater than 0, then we'll say that this is kind of destabilizing. And the 0 here is really the dimension of V dot theta. And just roughly speaking, if you're coming at this from a more geometric angle, this is kind of Mumford's stability criteria. And this theta is playing the role of the character. And you need a character of the general linear group to descend to this PGD that I defined. And that's kind of exactly this condition that the dot product with the dimension vector is 0. Okay, so from this definition, we now have a notion of V is theta semi-stable if no such W exists. Okay, good. Okay, and let's do an example. So we had before this kind of triangular shaped quiver. Let's add a stability condition 2, -1, -1. And these entries add to 0. So that's the statement that when I dot it with my dimension vector 1, 1, 1, I'm getting 0. And if I have V now, I'm going to write V as kind of a general representation. I need to worry about certain kind of destabilizing subrepresentations W. And so W could look like, for example, 0, C, C. I'll do this part in a different color so the maps don't get too confusing. This is a subrepresentation. I haven't actually defined this, but at the level of vector space, you take a subvector space, and then the linear transformations need to be restricted. You don't have a choice on them. And a different way of saying that is that if I take the inclusions up like this, all 3 inclusion maps, then this diagram commutes. This diagram commutes, meaning each face commutes. But actually, even in this small case, the diagram commuting kind of says different things. In the back right face, it's saying nothing with A. On the back left face, the diagram commuting starts at 0, so you're getting 0 both ways. But on the front face, it is saying something. So if you go left and then up, you're 0. So if you go up and then right, you need to be 0. So the diagram commutes if and only if B is equal to 0. And this is kind of a good thing. The point is the linear transformations being 0 means you have a lot of subrepresentations, things that can destabilize, but you can often turn on a bunch of representations to be non-zero, where there's you get like a semi-simple representation. You get something without, without destabilizing subreps. Okay, so this isn't the only subrepresentation you have to check, but if you check them all, what's the condition? V is theta semi-stable if and only if alpha and beta A and B are both not zero. And you can reinterpret this as I need the existence of certain paths in the quiver. So there exist paths taking me from the vertex before I called 1 to 2, and 1's taking me from 1 to 3. So from vertex 1, I need to be able to get everywhere else. And then in that case, I'm theta semi-stable. In the asymmetry, by the way, in this condition is coming from the asymmetry in the stability parameter. So by choosing the first vertex to be positive, I kind of distinguished it and broke the symmetry. Okay, and now kind of the open set I'm getting associated to theta is, it's just this. But the important thing to note is that it's kind of Zariski-open and that it's GD invariant. If you have something where A is not zero and you kind of conjugate, you're still going to have A not zero. Okay. And so I want to move towards research. But before moving forward, we actually have to take a step back. We're going to kind of think about stability conditions in a slightly different way. And then that different way of thinking about it is going to lend itself to this kind of theory. So the vague question, kind of too vague to be answered, is what is theta doing? Like, what is its role really in this calculation above, or even in general? Well, using theta, I can define a map. And what the map is going to do is it's going to take in the dimension vectors of my possible subrepresentations. So dimension vector. And the only relevant thing being kind of stable or unstable in this case was if you're greater than 0 or less than 0. And so it's going to assign kind of a symbol, +1, kind of plus or minus one of these two things. And the way it does this is taking W, you do the dot product, theta dot W, and then you take the sign of whatever comes out. Okay, so this is kind of a perfectly good map. And from this perspective, what's the open set? Well, it's the set of representations where there does not exist a subrep W whenever it's sent to something positive. So when this function on the dimension vector of W is plus. And we saw before in this kind of small example, this thing simplified to just saying that certain prescribed maps have to be non-zero. So kind of certain maps non-zero. Okay. And how do you know that you've removed enough representations and now you have something that's smooth? Well, you've done that. Oh, again, we're not quite ready for the example. So one more page. Oh, lost my spot. I added it to the wrong spot. Okay, sorry about that. What was I saying? How do I know I've removed enough stuff so the resulting quotient like this is smooth? Well, I need the action to be free. and this is going to happen kind of exactly when these non-zero maps form a spanning tree in my quiver. So I should just pause on this point because this is a very easy, like this is not a hard condition to check, and it's not really particularly hard to see why. I have some map like this, A, and as long as A is not zero, when I'm acting here and acting here, the action is going to be non-trivial unless G1 is equal to G2. So the action here is kind of trivial if and only if I'm acting by the same kind of scalar on both sides, and this remains true. So if I get a spanning tree of non-zero maps, then I'll be kind of acting freely and I'll be smooth. Okay. Maybe now we're ready for the main example, except I need to go back through this condition about what theta is doing, and I want to generalize it. And so the idea in generalizing it is just I can just write down any map that goes from theta to plus or minus, and I can make all the same definitions from before. So this definition still makes sense, just with S instead of S sub theta. And I can still kind of check this condition in the same way. And so the question of producing kind of more resolutions of singularities than what's given by stability condition is, can you produce more of these maps S than what's coming from kind of S sub theta? And so the answer is kind of very excitedly yes. And now we're ready for kind of the main example. So I'm going to go back to the slide format where I kind of talk you through some already written maths. Are there questions so far about this? Yep.
So I'm having a little trouble wrapping my head around this. So I mean, to me, the standard example should be when Q is a Dinkin-quiver.
Yeah. So Q.
So what
Yep.
happens, the dimension vectors correspond to like indecomposable representations. So that you get basically positive roots or something like that. And,
Yeah.
so all of this should have like interpretation in that setting. So can you like sort of briefly sort of explain how that works in the Dinkin-quiver situation?
Yeah. Sorry, let me try to explain. So
First of all, I assume it's been all worked out in the Dinkin-quiver situation.
yeah, but so yeah, so let me just think about the best way to answer. I mean, I have to basically I have to admit to the lie in that case. The point is the Dinkin-quiver example is things like this. Maybe one more. The point is all of the Dinkin-quivers are trees. So for the purpose of getting interesting spaces as representations modulo this group. Oh, I guess, sorry, this is something I didn't explain particularly carefully. So I guess it's a corollary of something I've already said. The key GD invariants are in the traces of cycles. And so if you're in the acyclic case, you can't get an interesting kind of moduli space of representations this way. The way you actually produce an interesting moduli space is by going to the extended Dinkin setting and looking at Nakajima quiver varieties instead of quiver varieties. So what Nakajima's construction is you start with a quiver Q, and everywhere you have an arrow, you draw an arrow back. And in doing so, you produce many cycles in your quiver. So it's richer now, kind of the GD invariance. You call that thing like this. And then in Nakajima's setting, you still have a dimension vector, you're looking at the double quiver, and now you're turning on certain relations as well. So the procedure I described above is to take a kind of a Zariski-open subset with stability condition, but you can take a Zariski closed subset too, just by saying, I want kind of this composition of arrows to be 0. So he adds a very particular relation that's kind of coming from the geometry. Like this. And then for the extended Dinkin quivers, the quiver variety you get at the end is the is kind of the Kleinian singularities, the Duval singularities from the beginning of the talk. And so if I want to make kind of my moduli space, then I can recover gives yeah, some kind of Duval singularity.
Yeah, so this is sort of the
Yeah.
classical picture that,
Yeah, so this is, if I was doing this talk kind of properly and motivating, building things up, this would be kind of the first example we could have and should have seen. And the reason we didn't is that from my perspective, this one just has a unique symplectic resolution. It's kind of projective, it's proper. And so to get more interesting resolutions of singularities, we start with a local picture where the local picture has kind of 2 interesting resolutions you can choose from, and then glue together many of these kind of local pictures. And that's the general framework. Essentially, it's a previous paper with Travis Schedler. We discuss how to build a large class of symplectic resolutions by gluing them on different neighborhoods. But the starting point is always kind of a conical singularity that has multiple resolutions of singularities to go off. This one has kind of a unique one, but this is already pretty important in the theory. So, okay, I'll leave this as kind of an aside. Kind of ADE Dinkin. Okay, and I want to talk a little bit about this main example, but are there other questions before I go into this kind of final example? Okay. Okay, so it looks like how I kind of described before. Vertex X and Y, and then 1, 2, 3, and 4 in the middle. And I want to, there's a little bit of kind of visual overload, but let me just break it all down. I'm drawing representations of these quivers where some arrows are undrawn, and what that means is the linear transformation is 0. Anytime an arrow is drawn, I'm taking just the identity transformation, kind of 1 here. And the reason that V12 is named this way is that starting from X, you can go to 1 and you can go to 2, and that's it. And these arrows are to be ignored for now, pretend they don't exist. And what's here is 4 different representations that are all singular in the quiver variety. And the reason they're singular is we don't have this spanning tree condition. The ones form kind of this component here and this component here. But I can act differently on those 2 components. So in the quotient, I'm getting kind of a singularity. For each of these representations, I write down its dimension vector here. So I'm starting at the bottom and then doing kind of 1, 2, 3, 4, and then going to the top. No, is that what I'm doing? It's the opposite. I'm starting at the top, then I'm doing 1 through 4, and then going to the bottom. And so this is the dimension vector just of this piece that contains X in it. So I have this piece containing X gives me this dimension vector. And then for V34, now the piece containing X gives me this dimension vector. Okay. And what I want to contrast, what the purple and green are going to do is there are two different ways of fixing these singular kind of representations by adding in a single arrow, a single non-zero arrow, to make them kind of smooth now within a quiver variety instead of singular. And so none of these blue representations are smooth, so they're not part of this kind of smooth set when I turn on the stability parameter. What this stability parameter is telling me to do is it's saying that it's saying kind of put a 5, a larger number at the top, and a 3, a smaller number at the bottom. And now that the top is larger, I always need green arrows going from top to bottom, from bigger to smaller. This was part of the definition of this set, is if something was positive, it couldn't be a subrepresentation, so I need to have arrows out of it. And yeah, this is always kind of going in one direction with the stability parameter, but I can make other choices than this, and that's how I'm producing other Zariski open GD invariant subsets. Is that instead what's happening with the purple arrows? Well, now I just make some choices. I decide that this representation is going to be minus, and that one's going to be minus, and then these ones are both going to be plus. This is plus, this is plus. And so the purple is kind of sometimes going up or sometimes going down based on the choices, but that's not something a stability parameter would ever do. And so in the interest of time, I'll just glaze over this, but it's a quick proof that this open set is genuinely something different than what you get from stability parameters, because the open set for stability parameters has to satisfy some kind of mild additivity that's not happening here. The point is, if I sum the two dimension vectors here on the left, I'm getting the two on the right. And so the green is consistent, it says go top to bottom on both, but the purple is inconsistent. It says top to bottom on the left, bottom to top on the right, but because they sum to the same thing, a stability parameter won't do that. Okay, let me pause because there's a fair amount of math in this main example, and let me see if there's questions. I've been going for a while now as well. Maybe actually in the interest of time, this is a good place for me to stop. Yeah.
Any questions?
Can you go back to the first slide?
Yeah, the very beginning with motivation. So I know scrolling can give a bit of a headache, but here we go. Yep.
We know how to classify semistable. So, do you think there's any chance to be able to classify symplectic resolutions, or, I mean, is that going to be like way too hard, or is there an easier problem? I mean, what's the status of that now?
Yeah, yeah, this is a really good question. So I would say yes, it's too hard, so it's out of reach for kind of modern mathematics. It's not going to happen in the next 5 years. If this is going on YouTube, don't quote me for this kind of stuff. But yeah, the status is that for these Nakajima quiver varieties, then there's two questions. I can hand you one and ask, does there exist a symplectic resolution? This has been answered. Then there's the question of, can you classify all of them? And in a large class of spaces, the point of the Nakajima quiver variety is that it comes with a stability parameter. So if I have a singular space like this, I can turn on some stability and get kind of a candidate resolution. And when I've turned it on in a way where things are smooth and where I get something non-empty, I'll get kind of a genuine symplectic resolution. And then the result is, if I have a dimension vector that has a single 1 in it anywhere, then all possible symplectic resolutions are given in this way by quiver GIT. And then you're trying to classify like what possible theta you can turn on. There's a wall and chamber structure. Then it's completely tractable. It's not really a hard problem anymore. There's other strange kind of O'Grady counterexamples where you have something that presents as a quiver variety. It doesn't have resolutions of singularities as quiver varieties, but if you kind of blow up a singular locus, you can get kind of something else. And so even for quiver varieties, this isn't kind of completely understood. And that would be the easier setting you should start in because you have combinatorial information and because you can describe each singular point in a quiver variety as a neighborhood of 0 in some other quiver variety. And this gives you a lot of mileage in terms of what the possible resolutions have to look like kind of around each point. So yeah, I would start with the Nakajima quiver variety setting. Good. Other questions?
Let's thank the speaker again.